ordinary. And here he received his master's degree in Brazil in 2006, right? And from 2006 to 2008, he's been working in the industry as industrial system designer. And since the end of 2008, he has been a PhD student at the Technical University here in Denmark, where he's working with research for innovative methodologies for Class D amplifiers for portable applications. Okay, so we have to switch to the PowerPoint. Okay, Gerd, please.
Okay, good morning. I am Gerd and I am starting my PhD study on audio amplifiers with Professor Michael Anderson and Mr. Lund as first supervisors. And this project is funded by the by Ice Power, 1/3 by the EDU and 1/3 by the Danish government. The motivation for this project is to produce a AC audio voltage swing which is higher than the battery voltage input. And the state of the art is accomplished this by using two stages, a boost stage and two books stages, or one book stage sometimes. And it has a characteristic of being very well studied control, very linear response to that cycle, and we use some commercial versions of this topology already available in the market. This study uses this double boost topology, which is accomplished by two boosts, and the load is put in the differential voltage of these two boosts. It has the advantage of being able to produce a voltage change higher than the battery voltage without an intermediary state, and it has the disadvantage of being very nonlinear. And the main purpose of this work is to try to work with this nonlinear behavior just with a control strategy. Some modes of operation were studied. This is which I call the asymmetrical mode, because it keeps one of the sides, one of the books short-circuited, so that the battery voltage is always in this point, while the voltage swings here for the positive semi-cycle, and then for the negative semi-cycle, the opposite happens. There's also the symmetrical mode, which accomplishes both the positive semi-cycle and negative semi-cycle just by regulating the duty cycle on both sides at the same time, and it has complementary duty cycles. And it was also studied an interleaved mode, which has this scheme for activating the switches. It has a characteristic of leaving the switch open for some time. So for certain periods of time, the load is kept held only by the capacitors, and it has some features. But In the selection of the mode of operation, because of the ripple voltage and ripple current, we selected the symmetrical operation mode. These graphs were made with the same duty cycle and exactly same operational characteristics. So symmetrical seems to be more efficient because of smaller people. This is the block diagram of the control strategy, which has a self-oscillating sliding mode control. It has a theoretical self-oscillating stage, and we can see in more detail here that the comparator acts directly in the gates, and as they have complementary operation, and a PAD compensator was used in order to accomplish the sliding mode, and there is voltage and current sensing in the output, and current sense accomplishes the inner loop in which the hysteresis is made, and voltage sense makes the compensation for voltage error in the output voltage. One interesting thing that was used was this inductor current sensing circuit, which doesn't interrupt the flow of current. It uses the internal resistance, intrinsic resistance of the inductor, and cancels the inductance using a capacitor, the effect of inductance. So I can measure in voltage here the same waveform and DC level of the inductor current. And this differential current is measured in order to make the hysteresis. The simulation environment was used, Simulink in Flex. It has some small disadvantage, but the main advantage of it is being very fast to develop new topology and try new things. The simulation results were very nice. The main goal in the beginning was to achieve a 2 times step up. So you can see that the voltage link here is higher than the battery voltage. The current sense shows that it's not a perfect triangle current, so it has some distortion, and it could lead to some distortion in the output, but it works and activates the comparator. And this here shows both the common mode output voltages for each boot side and the battery voltage for comparison. The simulation showed that a THD of 0.4 can be achieved by this control for 1 kHz and 14.4 volts peak to peak with a 3.6 volts battery. The measurements were made by mini-mount prototype. This is the latest version. It was made with an effort to minimize the size of the loop, of the power loop, so it doesn't have any ringing. And Here you can see